We often view the human body as a mechanical engine, a collection of parts that inevitably oxidize, rust, and grind to a permanent halt. If aging is strictly mechanical wear, medical intervention remains confined to localized repairs. We replace joints and prescribe pills to patch a system whose failure is considered a mathematical certainty. In laboratory experiments with the fruit fly, Drosophila melanogaster, researchers successfully doubled lifespans by altering the selective pressures acting on the population over multiple generations. This life extension was not the result of microscopic repair tools fixing cellular damage. It was achieved by manipulating the forces of natural selection to favor survival at later ages. Evolutionary biologist Michael R. Rose identified aging as a transient fall in age-specific adaptation, a state where our bodies stop adjusting to the environment because the pressure of natural selection has faded. Because physical decline is governed by these evolutionary parameters, we can utilize those same biological rules to shift our own physiological trajectory. This shift begins at the microscopic level with the Y model of resource allocation. Every organism operates on a limited energy budget. Evolution forces a physiological choice: invest those resources into early life reproduction or divert them toward long-term survival and maintenance. This graph illustrates the fruit fly trade-off. Researchers measured starvation resistance against fecundity. On the right, with abundant food, flies maximize reproduction, sacrificing durability. On the left, when food is restricted, reproduction drops. Energy is reallocated toward survival, dramatically increasing longevity. Human biology shares this allocative logic through hormesis, the application of low-dose stressors like intermittent fasting or exercise. These stressors act as metabolic signals. They activate sensors like AMPK and sirtuins, shifting the body's focus from growth to maintenance. While modern dietary abundance encourages our bodies to overinvest in short-term growth, we can use strategic hormetic stress to force the biological budget back into long-term survival. Understanding these trade-offs helps us manage our daily health, but we must also account for how our dietary needs change as we age. This chart tracks Hamilton's forces of natural selection. In youth, this force peaks, adapting our early life biology to process modern agricultural diets like grains and dairy. But after reproductive age, this force plummets toward zero. Evolution ceases to optimize our bodies for recent environmental changes. This creates a late life mismatch. Our older bodies lack the genetic adaptation to handle modern agricultural abundance, effectively reverting to an ancient hunter-gatherer physiology. Chronic diseases emerge when we provide a modern agricultural diet to a late-life physiology that still functions on ancient hunter-gatherer logic. By combining these insights, evolutionary biologists have developed a framework called SENSE, Strategies for Engineering Negligible Senescence Evolutionarily. The first pillar is the use of hormetic stressors, fasting and exercise, to signal our cells to prioritize internal repair over outward growth. The second pillar requires adjusting our fuel. To compensate for the drop in Hamiltonian forces, older adults can benefit from reverting to the Paleolithic diets their late-life biology is actually adapted for. While a younger body can often thrive on modern agricultural staples, this shift toward ancestral nutrition becomes a biological necessity as we age. These evolutionary mechanisms suggest that aging is a malleable state. By matching our lifestyle to the requirements of our ancestry, we use the body's allocative logic to sustain health deep into the human lifespan.